Hello, everyone. I'm Brandon Hill, University of Wisconsin-Madison. I'm excited to present our work, Geometry of Cortical Computation, Manifold Disentanglement and Predictive Dynamics in VCNet. In this work, we look at the gap between modern CNNs and the primate visual system. While CNNs are powerful, they're often data inefficient and brittle. We asked if we can bridge this gap by translating the macro architecture of the brain directly into a geometric deep learning framework. Let's start with key takeaways. First, we introduce VCNet. We interpret the visual cortex as a specific geometric engine designed to structure data. Second, we propose the brain's famous dual stream organization. The what and where pathways is actually a mechanism for manifold disentanglement. The network actively separates high-dimensional sensory noise into distinct low-dimensional geometric spaces. Third, we integrate this dual stream process with top-down predictive feedback. We move away from purely feed-forward passivity and implement active hypothesis testing, which we mathematically frame as a geodesic refinement on a manifold. And finally, the results. This approach allows VCNet to achieve state-of-the-art accuracy on complex texture and light field tasks, all while maintaining an incredibly small parameter footprint compared to traditional models. To understand the architecture, look at the blueprint, the primate visual cortex. Information flows from V1 and splits. Ventral stream, including V2, V4, and IT, handles object identity, the what, while the dorsal stream, including MT and MST, handles motion and space, the where. These aren't isolated, though. They interact. In higher areas, send predictions back down to lower areas. Core contribution of our paper is the geometric interpretation of predictive coding. Usually networks simply process input bottom-up. Here we start with the sensor representation in V1, derived from the actual bottom-up input. Simultaneously, the higher level area, AIT, generates a hypothesis. It projects a top-down prediction of what it expects the lower area features to look like based on its current internal model. When we compute the difference, the prediction error. We view this error as a vector in the tangent space of the manifold. This vector tells the network which direction to move to minimize surprise. This drives representation along the geodesic towards the true state of the world, refining the model dynamically. The second major principle is manifold disentanglement. Process input is entangled. In a high-dimensional space, the manifold of a cat and dog might be twisted together due to changes in lighting, rotation, or position. VCNet's dual stream architecture acts as a transformation engine. The ventral stream attempts to flatten the manifold to be invariant to pose, keeping identity constant, while the dorsal stream learns manifold equivalent pose for spatial relationships. The result is a representation where semantic categories are linearly separable, making classification robust and efficient. We test this on the SPOS10 dataset. This dataset requires recognizing complex natural textures, that's central to primate evolution for predatory and prey detection. VCNet achieves 92.1% accuracy, beating the distilled DenseNet 121 by over 10%. And looking at the x-factor, the model is 43% smaller than the baselines, showing the right inductive bias. It gets extreme efficiency. We also want to test the model on data that is richer than the standard 2D images and more like what a biological visual cortex might interpret. So we used light field data. Humans see in 3D with depth and parallax. Light field cameras capture this angular information. We hypothesize that our dorsal stream would excel here. In the light field classification task, we see that it achieves 74.4% accuracy, significantly outperforming MobileNet and ResNet DEX. Again, note the efficiency. We says much smaller than the baseline models, which validates the architecture methods of disentangling view-dependent information. In conclusion, VCNet demonstrates that we can build better AI by looking at the brain through a geometric lens. By explicitly engineering manifold disentanglement predictive coding, we achieve robust, highly efficient models. Moving forward, we plan to integrate explicit equivariance using stirral filters in the V1 block. Use topological data analysis to formally quantify the manifolds we are learning, and extend dorsal stream dynamics to full video processing. Thank you for your time. Please scan the QR code here to read the full paper.